Thank you. Well, I'm very honored to speak here. Is this okay? I think it's. I would like to talk about this special type of fibrations. Um, and the motivation is actually to understand singularities. And I would like to say a few words about this singularity. So if you have a singularity, which is not so bad, in fact, these are so-called Q-Gorenstein singularities, some multiple of the canonical classes Cartier. Then one can define an invariant number, which is called the minimal log discrepancy. How do you define this? You usually take x. Uh, ah, you take a resolution of singularities, and then you have the canonical class downstairs, the canonical class upstairs, and uh, you pull up the canonical class, and it will differ from the canonical. Is there a problem with it? It will differ from the canonical class upstairs in some divisors, sum of alpha I ei, let's say, and then 1 minus alpha I is called the discrepancy in ei of x. So these log discrepancies in the prime divisors which appear on resolutions. And we take all the resolutions, and we have all these prime divisors, there are infinitely many, and we take the infimum after all these. This infimum is either minus infinity, or this happens only when the singularities are not canonical. But if the singularities are log canonical, it's a real number between 0 and its conjecture to be at most dimension. This is a conjecture of Shokurov, but this is not known. The conjecture is that the minimal log discrepancy is at most a dimension, and it's equal to the dimension if and only if it's a smooth point. If you have a smooth point, the minimal log discrepancy is exactly dimension. Okay, so one would like to understand this invariant of singularities in connection with the minimum model program. There are certain conjectures of Shokurov on this invariance, minimal log discrepancy, also global versions. These are related to indices of low Calabi-Yau varieties or to complements, something that when you have a Fano, you try to put a structure of Calabi-Yau on it. So if one understands these questions, which they involve minimal log discrepancies, one should be able, in theory, to prove determination of the minimum model program. So this is the motivation for understanding this minimal log discrepancies. Okay, so not much is known in dimension 2. These are understood minimal log discrepancies. And in dimension 3, partially, like terminal or canonical singularities. In any dimension, we only have the toric case, which has been settled by Borisov. And this is his theorem, which says that if you fix the dimension at some threshold t, then among the toric varieties with the minimal log discrepancy in that point to be at least assume they're also Q-factorial, then they belong to finite many series. So this was based on some, so this is some qualitative statement which was proposed after some work of others who tried to classify terminal singularities in dimension 4, terminal cyclic singularities in dimension 4. And this is a very nice theorem, which is in fact based on some combinatorics. There is no geometry in this theorem. It's just combinatorics. But we would like to have some geometry. So one nice corollary of this structure theorem is that this minimal log discrepancies satisfy ACC. So you cannot have an infinite sequence which accumulates from below of this invariance minimal log discrepancy, which we have defined above. This happened in the toric case. Conjecture is that it is conjecture that this is true in non-toric case as well. So the main question is that first of all, these series are combinatorial. I will explain how are they defined. And we would like to find the geometric meaning. Do they have some geometric meaning? Do they exist for non-toric varieties? Because if they do, then they will have major implications in the study of singularities. So these are the motivating questions. Okay. So in this talk, I will. What is new compared to Borisov? First of all, we will show that this assumption Q factorial, this assumption here that x is Q factorial is redundant. We remove it. This is one thing. And another thing is that we actually show that in order to understand this series, one has to enlarge this category. Instead of working with singularities, we should work with a larger category of Fano fibrations. And you may realize any singularity as a Fano fibration by just looking at the identity map, X over itself. So this would be the next step. And okay, so what we will try to do is to extend this series of Borisov to these Fano fibrations. We remove these Q factoriality assumptions, and then we will discuss some applications of these results to some conjectures of Shokurov or complements. Okay, so basically this is the plan of the talk. If you don't have any questions, then I'll move on. Okay. So I should. There is a warning here that this is not quite the theorem of Borisov, because actually in Borisov he's concerned. This is minimal log discrepancy you see over P here, which means I only look at valuations which are centered at P. In Borisov he looks at all the valuations, but the statement is a bit more complicated. This is somehow the the statement in pure type. The statement of Borisov is like a gluing of this. It's not stated in Borisov, but it's equivalent to what he wrote in his paper. So in our setting, we only focus over a point. Yes, we do not look at all the valuation. Okay. So let's see how do we explain this series of Borisov? These are based on some very nice theorem in combinatorics, which says that if you have a torus, you have a real torus and an open subset, you consider all the subgroups which avoid that open subset with respect to inclusion. So this set can be ordered with respect to inclusion, and the statement is that the maximal elements are only finite. There are only finitely many maximal elements. Yes. The proof is non-trivial, but not very difficult. But one needs some statements. There are some non-trivial arguments behind. For example, let's take a look. What if we fix V to be 0 epsilon inside R? What are the groups which avoid this set? So there are just the maximal ones. Of course, 0 does not avoid it. 0 does not intersect it. But the other ones are just the one kz, where k is bounded. It's a natural number between 1 and 1 over epsilon. bit more interesting is what happens in dimension 2. You take the standard simplex, yes, with the vertices 0, 0, 1, 0, 0, 1, and you take the interior of this. And the question is, what are the maximal subgroups of the torus which avoid this open subset? And it turns out there are exactly three. This 1, 0 star, 0, 1 star, 1, 1 star. But whereby star we mean those x, those elements x, such that x times the, for example, here it's 1, 0, it's integer. So this is x1 plus x2 is integer. This means that x1 is an integer, and the other one is that x2 is. If you go one dimension higher, it's a bit more complicated. In three variables, you look at the standard at the interior of the standard simplex. So you look at the subgroups which avoid this open set, subgroups of the torus. So you may also think of them as the subgroups in R3 which contain these vertices, yeah, instead of going down to the quotient. And one can use computer. This is not proved, but the computers suggest that these are all. So the maximal elements are, first of all, 1, 0, 0 star, which means that x coordinate is an integer. 1, 1, 0, 1 star, 1, 1, 1 star. So these are given by one equation. Yes, just like the ones here. Here we also have one equation. And then we have two equations in this in this case it's 0L2 star intersected with 210 star, where L can be 0, 1 or one more intersection, or you have three equations, but a bit more complicated, but they're finitely many, this type of solutions. Okay, so basically this is the this is how you should think of this series of these maximal elements. They're given by some equations like this, and here is the proof of the theorem of Borisov. Yeah, so the statement is the one we saw before, and let's see the proof. So. Well, we take a toric variety with an invariant point. It's simplicial. What Q-factorial, the Q-factorial assumption is that we have coordinates. It's just a quotient of the affine space. So in this case, we may normalize and we may suppose that the cone defining the variety is just the standard positive cone. And the lattice is just an extension of the usual one, a finite extension, such that the standard basis remains primitive in the lattice n. And then you recover x just as the quotient of the affine space modulo this quotient, g of x, which is n over z to the d. Everything is very explicit. And then in this setting, you look at the standard positive cone. You look at the standard positive cone and all the lattice points which are interior to the cone, and you have this height function, which is the sum. For each point, you associate the sum, and then you slide it up until you hit the first point in the lattice. That's the minimal log discrepancy. This is how you compute the minimal log discrepancy in this case. And it turns out that in order to compute this point which will compute the minimal log discrepancy, will always have coordinates between 0 and 1. Cannot be higher than 1. There is a small argument to prove this. So you see this x is in bijection with this lattice, which is in bijection with this quotient n over z to the d, which is a finite subgroup of the torus. And we denote by u the standard simplex. In this case, it's this complex set. And it turns out that the condition that the minimal log discrepancy at P at X is greater than 2 is equivalent to n to the interior of T times U containing no lattice points. But this is the same as this going down to the torus. This is the same as this saying that this quotient belongs to this set of subgroups which avoid T times U, the interior of T times U. And then by Lorentz theorem, there exists a maximal group which contains this, and this belongs to finitely many choices. So this is the series of TLC toric Q-factorial singularities. Okay, so let's see an example. So the first example is these are canonical singularities in dimension 2. So we assume that the minimal log discrepancy is at least 1. And in this case, we have just 1, 1. We have just 1, 1, which corresponds to the smooth point, or the points which should lie on this equation. We have no, theoretically we also have points here, but because we assume that the boundary is 0, this is not possible. So they could just be here, but not any point. Again, the boundary is 0, so therefore they're only possible are points which are of this form. Yes, 1 over k and k plus 1 over k, which approach the boundary when they become infinite. And then these are just the AN type of singularities, yeah? Okay, so how about also in dimension 2, but we dropped the level. Previously T was 1. We drop it to 1/3. If we drop it to 1/3, picture becomes more complicated, but theoretically, I mean, practically, it's very simple. So we have these lines. So for example, if we have the minimal of discrepancy at least 1/3, which is this level, yes, then you look at all. You look at 1, 1 over half, 1 over 3, up to this level, and you join this segment. And then you have on this green lines, you have points accumulating. You have points accumulating to the boundary, like this guy. Yeah. Nothing accumulating to the interior, but you will also have some isolated solutions. If you put 1/2 instead of 1/3, there are no isolated solutions. But in this case, there are. So, for example, this 1 over 19. 3,4 and 1 over 23, 3,5. So there are two. They break up in two types. These solutions. These are in fact they are isolated when we take this threshold 1/3. But as you lower the threshold, they will become part of another series. So this thing is like a truncation. So we truncate when this T. This T, when T goes to infinity, you obtain them all, but fixed T, somehow you you truncate this series. Okay, so now my original motivation was to understand this series of Borisov in the non-Q-factorial case, when you don't have this coordinate. And the first step was to find the definition of series which does not depend on the coordinates. So here is the definition. One can do this, and let's see this series of Borisov. We consider these subgroups of R to the D, which contains Z to the D, same as looking at the subgroups of the torus, and G avoiding the interior of some open set T times U. Now, because G is maximal, it must be closed. And if it's closed, then there is a duality theorem which says that G is the dual of its dual. So you can recover G if you know the dual. Yes? But what is the dual? The dual is much simpler than G. Can have real components and so on. But G is the dual is a subgroup of the dual of D. So it's a free abelian group. We choose a basis. So if we choose a basis of this dual abelian group, this induces a projection from R to the D to R to the R, where R is the rank of G star. And the thing is that our initial group is just the preimage of the standard lattice with respect to this projection. Okay. So because G is pulled back from the image of this projection, the fact that G does not intersect the interior of this TU is the same as the standard lattice downstairs does not intersect the image. Yes, so we somehow push down everything to the image, and what happens? We denote by U prime the image of phi and the image of U under this projection. Remember, U was the standard simplex. Yes, was the convex hull of the origin and the standard basis. And the fact that the minimal of discrepancy toric variety is at least equivalent to the fact that there exists some by some lattice n which is contained in G, and that there exists such a projection. Yes. But now let's look a bit closer. So the image originally U was contained the origin as a vertex. Yes. If you remember, so this was the original. Yes. E1, E2. But when we project, the thing is that when we project U prime, 0 may be on the boundary here, so it may not be vertex. This is one difference, but it will contain 0 anyway. So the other observation is that the quotient of z to the r by n prime is a group of bounded index. Because these series are finite. Okay, and now the fact that G belongs to a finite collection is the same as the entries of this basis are integers with bounded absolute value. And then if you work this out a bit, it turns out that this is equivalent to the fact that this image Tu prime is contained in a bounded box, in a box with a bounded length, which is the same as saying that this pair is bounded. Let's give a definition here. So we say that a pair consisting of a lattice and a convex body is bounded if there exists a basis of the lattice such that with respect to that basis, the body is contained in a box of bounded length. Yes, a length bounded above. So now we can have a dual reformulation of this of the finiteness of Borisov series. And the formulation is that if you have a toric log variety, we take U to be the convex hull of the origin and the primitive generators of the cone, and some fixed T. And the statement is that the minimum of discrepancy is at least T, if and only if there exists some projection such that if you take U prime to be the image of U under the projection, then we have two properties. First of all, there are no interior lattice points in Tu prime. And secondly, this pair is bounded, N prime Tu prime. The proof by, we cannot apply Lorentz theorem here because we have no coordinates, so it's different. If T is rational, this follows from a result of Neal and Ziegler from 2011, which I will recall this statement because it's somehow to this existence of series. So we fix the integers D and L, and we take the d-dimensional polytopes in RD with vertices rational and of index at most L. Indices dividing L. And the statement is that this polytope does not contain any lattice point if and only if either it belongs to a bounded family, to a finite isomorphism type, or there is a projection such that the projection satisfies the same property. And if there is such a projection, then the polytope itself will satisfy this property. Yes? So somehow this is similar to this existence of series. For example, look at this polytope, which is contained between y equals 0 and y equals 1. If you can take it arbitrarily long, but it will not contain lattice points in the interior. But you can find the reason for this is that its projection contains no interior lattice point. So when you project over there, you see that the projection is 0, 1, and because 0, 1 contains no interior lattice points, none can be contained in the stripe there as well in the interior. Okay, so now what is the geometric interpretation of these pairs, n prime to u prime, given by the projection? If you remember, we started with some singularity, and we associated u, which is the convex hull of the primitive generators and the origin, and we took this projection. But as I said, that when we take the projection, the origin is no longer a vertex. It's on the boundary. Yes, it's on the boundary, but may not be vertex. So, for example, in dimension 3, the projection can be one of the shapes you see there. So one of the statements is that 0 is on the why it's not in the interior of the origin is that because this image contains no interior lattice points. So therefore 0 is on the boundary. Another difference is that the vertices of this image U prime are just in the lattice, but maybe not primitive anymore. Yes. This is because when you project, the lattice point will no longer be primitive after projection. So here is one example. So let's suppose that 0 is still it's still a vertex. But in this case, this is not a simplex anymore. You may have several cones breaking up the standard cone, but you can associate to this a birational log Fano structure. And how do you do this? This is just by forgetting the subdivision. This is the toric morphism. And the log structure is induced by the multiplicities from these generators. So you see the vertices of U prime are no longer primitive. There are some multiple primitive, and these multiples correspond exactly to the log structure. And one can show that the minus k minus b is relatively ample. The minimal log discrepancy in the special fiber is at least t. And the last fact that the pair between the lattice n prime tu prime is bounded is equivalent to the finiteness up to isomorphism of these structures. Yes. So you have only finitely many birational morphisms like this. Or you can project over a one-dimensional base. This is A1. This is the only possibility. And you have the same thing. So vertices are multiple of primitive vectors, and they induce this log structure. And the same properties hold. So you get minus k minus b relatively ample. The minimal log discrepancy in the special fiber is at least t, and finite isomorphism types. So this is the interesting observation, is that this series of Borisov, they correspond to finitely many log Fano fibrations. Yes, although we started with singularities, we started with some singularities. And then Borisov explained these singularities in terms of series, which are subgroups of the torus. But if we look at the dual, if we look at this series dually, you see them. We can see that they correspond to some Fano fibration. This is the argument so far. Yes. So we started off with a singularity, which you can think of it as a Fano fibration just by taking the identity here, and then we constructed some yes, and okay. So the main question is, does this make sense in the non-toric case? Because everything is combinatorial here. Yeah? So we don't use any geometric argument yet. Basically, we just, yeah, so we use combinatorics. But the objects are geometric, both here and here. And in order to get this reduction, we use combinatorics. So can one get rid of the combinatorics? Okay. Any questions? Okay. If not, then let's see the main statement. So we can generalize the theorem of Borisov to Fano fibrations. And this is the main statement, that if you fix some integer d and t, both positive, and some set satisfying the descending chain condition, we take a toric morphism with base affine and with an invariant point p. We assume that the dimension of the base is at least 1. And we take B to be an invariant divisor, which has coefficients in this DCC set from the start. Invariant just means that it's supported by the complement of the torus. We have a so-called moment polytope of the anti-canonical divisor, and we take U to be the dual. The notation is compatible with what we've seen before. U is just the same as before. Then the following are equivalent. First of all, there exists we can increase this B to a local Abiyau structure. So we can find some B plus, such that K plus B plus is torsion. And the minimal log discrepancy over the special fiber is at least T. Yes, this is a very geometric condition. And the second one is combinatorial description. And this is equivalent to existence of a projection such that the image is compact, because I mean originally this may not be compact U, but when we project the image should be compact. And again, the interior of Tu prime has no lattice points, and also this pair is bounded. Okay, so this is the main theorem, and it's equivalent to the finite subseries. Yeah, and first observation is that this is equivalent to the property that Tu prime has no interior lattice point. And under those conditions, the theorem just says that one has a projection where everything becomes bounded. This is the main thrust of the theorem. Yeah, so it's similar to this theorem of Neal and Ziegler. And the proof is combinatorial. The method is the method of Kanan and Lovatz to use reduced basis. Somehow and somehow canonical. This projection can be constructed in a canonical way. It's just contracting chords of maximal length and then iterating. And this combinatorial proof is based on two main statements in combinatorics. One due to Picurco, and the other one Neil Ziegler. And let's see, what are they? We take a lattice n, which is isomorphic to z to the d. We take a polytope inside the real extension, which contains the origin. Yes, here is this polytope. And then we assume that for every, so we assume that the vertices are of special type, not every vertex is allowed. So we assume that if V is a vertex, which is non-zero, well, it's either zero, or if it is non-zero, then it's of this form, E over A to the E, where AE is positive in an ACC set. And there are two statements that need to be proved. First of all, if such a polytope contains a lattice point in the interior, then it contains at least one which is kind of central. So I won't get into details, but basically they cannot all lie close to the boundary. There must be one which is central. And the second statement is that if there are no points, no interior lattice points, then there should be a bounded projection with bounded image and the same, and almost the same, okay, in this setting, the same properties. So somehow these are the two combinatorial statements that need to be proved: the centrality of interior lattice points, and then this existence of a bounded projection. And the same way, same as in the case of singularities, when associate toric lock structures, the toric lock Fano structures. So now of the singularities, we stay in the same category. We have Fano fibrations, and we end up with Fano fibrations. And this series of Fano fibrations should be expanded by a bounded number, by some fibrations which are bounded. Okay, so let's see some applications of the main theorem. So first of all, we take let's take a toric morphism. B is an invariant divisor with standard. So standard just means P1, P minus 1 over P, where P is greater than 1 or 1. And we assume that there is a local Abiyau structure here, which is nice. So there exists some B plus, which is at least B, such that K plus B plus is torsion, and the minimal log discrepancy over the special fiber is at least T. Then the same way that there exists such B plus, such that the index is bounded. So n times K plus B plus is trivial, and n depends only on the dimension and T. Yes. So this is a complement. Another another application, and this is a new type of statement, is that if we take fibration just as in the theorem, we further assume that minus k minus b is f semi-ample, and the minimal log discrepancy of the special fiber is at least t. Then the same is that there exists downstairs some bounded hyperplane. So there exists some hyperplane with good singularities above. So there exists some H, which is an invariant hyperplane, such that when you pull it up, then K plus B plus gamma times this pull up has low canonical singularities, where gamma is positive number, which depends only on the data. I mean, only on D, T, and the coefficients, but not on X and Y. Yes. The third application is that if we fix the minimal log discrepancy, we assume that B has DCC coefficients, it's invariant, the X is toric, and we also fix the dimension. And then if the minimal log discrepancy belongs to a DCC set, then everything is bounded up to an A reduction. So instead of T, I can choose T equals A here. And then in particular, this implies that A, first of all, belongs to a finite set. So A may accumulate from below a priori, but this is not possible. The coefficients are also finite. This is equivalent to the ACC of T log canonical thresholds. Also, if B is rational, it follows that the index of K plus B is bounded independently. I mean, depending only on dimension and the DCC set. Okay, so let's see some final questions. Um, the main point of this talk is that starting off with some toric Fano fibrations and assuming that the central fiber has T log canonical singularities, there exist finite domain series, and these series they correspond to some other Fano fibrations which belong to finitely many types. But this correspondence is constructed combinatorially. So can one do this geometrically? In the toric case. And also, can one do this outside of the toric world, also for non-toric varieties? I think this would be very interesting, and if true, then it will have very important application. This is the main question, and then also it's interesting, I think, to attack the original setup of Borisov, where he takes into account all the valuation. Yes. In other words, he takes valuations which are not only centered at one point, but they're centered through the given point. But somehow this is a gluing of our setting, but it should be decided somehow. So how about this original setting of Borisov? Can one do the same when we assume the global minimal of discrepancy to be bounded from below? Yeah, so okay, so basically this is to say. Thank you.
Main theorem.
On the
Main theorem.
main theorem, okay. Okay. Here?
Yeah. I think that if I understand it correctly, it seems that this means if I have the original final vibration is epsilon log canonical, then I can get a epsilon log canonical complement, bounded complement.
There are no complements here. This is just, the main theorem is just a combinatorial restatement plus the fact that there exists a bounded projection. Complements are here. Complements are here. In one, here. But usually you don't get effectively epsilon log canonic. You get epsilon TLC, but yeah. This is what you mean. One. Yes. Yes.
Okay. My question is, it seems that often in non-toric case, we often work with epsilon, also then we get maybe like delta at the canonical. And in toric case, we can get the standard estimates.
No, conjecture is that there should be also delta equals to epsilon. Yes. This is actually, this was a conjecture of Shokurov. Is a conjecture. This is a solution to a conjecture of Shokurov in the toric case. Conjecture that is true in non-toric world. Yes. So it's not necessary to go down, like epsilon delta. It should be true when you fix the threshold epsilon.
Thank you.
Yeah. I have no idea. Probably it's doable. Yes. I think, yeah. If one wants to know if it's true in a non-toric world, it should be doable. Yes. I mean, if it's doable, it should be doable there. Yeah. Yeah.
Any other questions?
The final question, are there any special cases? The final question you asked,
Final question.
yeah, are there any special cases or examples?
You mean for the final questions? No. Even for surfaces, this is not known. Yes. No, I mean, no, this is known for toric. You mean to find a non-combinatorial? Yes. So it's not known even in the toric case. So this is known through combinatorics. We use combinatorics. Is there some geometric construction which does this? Yeah, like hyperplanes and anti-canonical members, something like this. So one should construct some hyperplanes or anti-canonical members, some linear systems inside here, in some multiples of anti-canonical class, and using some geometry, use this to induce this. So by this I mean, but this is not known. So somehow this suggests that these toric Fano fibrations with Mirabok discrepancies of the fiber are bounded below. They are finite isomorphism type modulo some reduction. This is the statement. How this is the reduction, yeah? So this reduction is only known combinatorially. Can we define it without combinatorics, just geometrically? This is the, and I don't think it's that hard actually, but we don't know yet.
Then let's thank the speaker again.